When beginners hear the word container, they often picture a tiny virtual machine, like a small box that holds an application and keeps it separate from everything else. That picture is not totally wrong, because containers do isolate things, but it is also misleading in ways that can cause confusion on the exam and in real troubleshooting. A container is not a full separate computer with its own kernel, and understanding that difference is one of the most important foundations for container thinking. Containers rely on the Linux kernel, and the isolation is created by kernel features that separate what a process can see and how it can use resources. The thing that makes containers practical at scale is that they start quickly, share the host's kernel, and are defined in a way that can be reproduced. In this episode, we focus on two core ideas that make container concepts click: the role of the container runtime and the boundary between an image and a running container. If you can explain what a runtime does and what it means to turn an image into a container, you will be able to reason about most exam-level container questions without getting lost in brand names. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A container runtime is the software layer responsible for creating and managing containers on a host system. If you think of a container as a control process, the runtime is the manager that sets up that control. It prepares the isolation environment, starts the process, and keeps track of the container's lifecycle, including stopping it and cleaning up resources. The runtime also understands how to pull and unpack container images, which are the templates that containers are created from. Beginners sometimes assume the runtime is part of the container itself, but it is more accurate to say the runtime is part of the host, acting as the system that builds the container environment around a process. That host role matters because the runtime is also the bridge between container expectations and host reality, like network access, storage, and security settings. At exam level, the main point is that containers do not appear out of thin air. Something must translate a stored image into a running, isolated process, and the runtime is that something. To make this concrete, it helps to compare the runtime to a stage crew in a theater. The actors are the application processes, and the audience sees the performance, but the stage crew builds the set, controls the lighting, and ensures the scene changes happen smoothly. The runtime sets up namespaces, which are kernel features that give processes separate views of things like process IDs, networking, and mount points. It also applies control groups, which are mechanisms for limiting and accounting for resource use like CPU and memory. These features allow a containerized process to behave as if it is in its own small world, even though it shares the host kernel. This is why containers can be lightweight compared to full virtualization, because they do not need a separate operating system kernel per workload. The runtime orchestrates that lightweight isolation, and it also enforces the policies that define what the container is allowed to do. For beginners, it is enough to remember that the runtime creates and enforces the boundary between container and host. Now we can talk about the image and container boundary, which is one of the most useful mental models in container fundamentals. An image is a read-only template that contains the file system content and metadata needed to start an application in a predictable way. Think of it as a packaged snapshot of what the container should look like at start time, including the application binaries, libraries, and default settings. A container is what you get when you take that image and run it, meaning the runtime creates a live instance based on the image and starts a process inside the isolated environment. This relationship is similar to the relationship between a class and an object in programming, or between a blueprint and a built house. The blueprint is static and reusable, while the house is a specific instance that can change over time, be occupied, and eventually be torn down. At exam level, the key is to never confuse the reusable template with the running instance, because many container behaviors make sense only when you keep that boundary clear. A big part of the image versus container distinction is mutability, meaning what can change and what is intended to remain stable. Images are meant to be stable artifacts, and they do not change when a container runs. A container, on the other hand, can change during runtime because processes can create files, write logs, and modify state inside the container's writable layer. That writable layer is one reason containers feel like little machines, because you can install additional things or modify files within a running container. The trap for beginners is to treat those changes as durable, because many container workflows assume containers are disposable. If the container is deleted, its writable layer disappears unless the data was stored outside the container in a persistent location. This is why you will hear the idea that containers should be treated like cattle, not pets, meaning they should be easy to recreate rather than carefully maintained by hand. You do not need to adopt that philosophy completely to understand the exam, but you do need to know that the image is the source of truth, and the container is an ephemeral instance unless you deliberately persist data. This boundary also explains a common beginner confusion about updates. If you update a container by changing files inside a running container, you have changed that one instance, not the image template that future containers will use. If you want the change to be repeatable, it needs to be reflected in a new image, because the image is what is shared, stored, and pulled onto other systems. The runtime uses images as inputs and creates containers as outputs, and that one-way relationship is a core part of container predictability. The exam often tests this kind of reasoning by describing scenarios where changes disappear after restart or redeploy, and the correct explanation is usually that the changes were made in a container instance rather than in the image or in persistent storage. When you keep the boundary clear, these scenarios stop feeling unfair. They become a straightforward consequence of template versus instance thinking. Another fundamental idea is that containers share the host kernel, which gives them speed and efficiency, but also shapes their security boundary. Because the kernel is shared, container isolation is strong, but not the same as having a separate operating system kernel like a virtual machine. A vulnerability in the kernel can potentially affect containers on the host, and misconfigured container privileges can weaken isolation. At exam level, you should understand that containers are not magic sandboxes. They are processes with boundaries enforced by the kernel and the runtime's configuration. This also means host configuration matters a great deal for container safety. If the runtime is configured with overly broad permissions, a container might access host resources that it should not. If the runtime enforces least privilege, containers can be very effective at reducing the blast radius of an application compromise. The key takeaway is that containers rely on kernel features for isolation, and the runtime decides how those features are applied. Networking and storage also become clearer when you keep the runtime and boundary concepts in mind. A running container needs some way to communicate, and the runtime sets up the network view that the container sees, which can include its own virtual interfaces and routing rules. The container also needs file system access, and the runtime provides that by assembling the image file system plus a writable layer for runtime changes. When data must persist, you typically need storage outside the container's ephemeral writable layer, because the container layer is meant to be replaceable. These ideas will be explored deeper later, but the fundamental point is that the runtime is the one doing the assembly and wiring. The container is not self-sufficient. It is a managed instance that depends on the host's runtime configuration to define what it can see and how it can interact with the outside world. Understanding that dependence helps you reason about failures that might appear to be inside the container but are actually caused by host-level constraints or misconfigurations. A beginner-friendly way to summarize the container mental model is to think in 3 layers. The host system provides the kernel, the runtime provides the container environment, and the container process provides the application behavior. The host kernel is shared, so kernel-level changes and policies affect all containers. The runtime sets up isolation, resource limits, and integration points like networking and storage. The container is the running instance created from an image, and it can be started, stopped, and replaced. The image is the package template used to create those instances, and it is meant to be reused and distributed. This layered thinking helps you identify where a problem might live. If an application fails inside a container, it could be the application itself, the image content, the runtime's configuration, or host-level limitations. You do not need to solve every issue to be exam-ready, but you do need to know how to place an issue into the right layer. To close, container fundamentals become much less intimidating when you anchor on 2 concepts. The runtime is the manager that creates container isolation, and the image versus container boundary that separates reusable templates from running instances. The runtime is part of the host and is responsible for turning images into running, isolated processes using kernel features like namespaces and control groups. An image is a static, read-only template that contains the file system content and startup intent, while a container is a live instance created from that image with a writable layer and runtime state. Containers share the host kernel, which gives them efficiency and quick startup, but also means their security boundary depends on correct runtime configuration and host kernel security. When you can explain these ideas clearly, you can interpret most container behavior without guessing, and you are ready to learn the next topics that build on this foundation, like image operations, running containers, storage persistence, and container networking.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.